Hello everyone, I am Doğuhan, doctoral candidate number 8 in the GECKO doctoral network. In this video, I will talk about my research progress up to 22nd of May. My main objective is to do efficient transient unbounded acoustic analysis starting from CAD designs. For the numerical acoustic part, there are two main options, finite element or boundary element methods. Each has its own advantages and disadvantages. For the transient or the time domain part, finite element has time stepping method which has better scaling than time marching used in boundary element. For the unbounded domain part, finite element requires special boundary condition treatments while it is already automatically included in the BAM formulation. For the modular reduction part, finite element matrices can get much smaller but they lose their sparseness property, while reduction for BAM is smaller, but they are already dense. For the IGA type discretization workflows, finite element generally requires immerse type method since obtaining a volumetric mesh in IGA is a bit problematic, while boundary element is already IGA ready, but it has its own problems. We have focused more on the boundary element side, and now I will talk about the general formulation of it. We start with the acoustic wave equation. We apply a weighted residual formulation with a convolution. Convolution is there to take care of the time domain part. When we apply integration by parts once, we get the weak form, which is generally used in the finite element methods. However, if we apply another integration by parts, we can move our derivatives on the primary variable to our test function, and we can get some initial and boundary condition alongside it. And using this strong form equation of motion, we can choose our weighting or test function to satisfy the equation of motion if our excitation is an impulsive forcing at a single point. So that our test function becomes the fundamental solution, and when we replace it in the domain integration, we can get rid of the integration and just obtain the pressure at some time and space, and this is called the representation formula, which allows us to construct our volumetric solution from the known boundary values. But in this form, it does not actually help us solve the unknown boundary values. For that, we need to apply a limiting procedure to our pressure to go onto the boundary so that we can start to solve for boundary unknowns using the known boundary values. And this equation looks like this. And when we discretize it, we can get the equation of motion, such as this one, where our current time step is obtained by using the contributions coming from the current time step, as well as the contributions coming from the past time steps. This is due to the nature of the convolution. If we use equidistant time step, we can simplify it a bit, and we can construct a large system of matrices such as this one. And the solution can be done step by step, where we solve for our current time step and replace it in the next time step solution on the right hand side, so that we can obtain the next time step solution at the current time step. The main drawback is that we need to construct and store all the system matrices for all time steps, which makes our scaling for storage that depends on the number of time step alongside the square of the number of degrees of freedom. And for computation, this time step dependence becomes a square. Now we can look at an example to analyze this method. We apply normal velocity is equal to 0 on 3 edges of a rectangular geometry, and we apply a step pressure on the right hand side to see the response as in the animation, and we can compare it with an analytical solution, and we can see that it matches closely with the analytical result. However, it is still harder to capture these sudden changes of pressure, and also there is numerical damping at the end. And this numerical damping needs to be optimized on the problem basis so that it does not cause instabilities or very high numerical damping. Now we can look at the solution acceleration options to increase our solution speed. So we start with our fundamental solution in 2D, and we can see it is not defined with respect to time. So it means that we cannot separate the distance and the time components of the fundamental solution, which makes our scaling unfavorable. And we decided to expand this fundamental solution around the representative distance so that we can separate our distance calculations with the time calculations. And this representative distance is taken to be generally the average distance of the geometry. And with some manipulation, these convolutions can be truncated after some time limit so that we can disregard the matrices obtained that needs to be obtained in those time steps, and instead replace all of them with our series expansion. So this A star system matrices are comprised of series order expanded system matrices that depends only on the distance or the powers of the distance and some temporal function. Now to see an example, we consider a maximum error in terms of comparing it with the full solution to the reduced solution, and we take the maximum error in time at 3 different points in the geometry of the 1D bar example, and we can get a graph such as this one where we have plotted error against the delta parameter. This delta parameter depends on where we cut off our fundamental solution, and it basically means the increase in the delta parameter means we start our truncation earlier, so we include less matrices in time and replace them with the Taylor series expanded matrices. And we can see as we increase our approximation order, we can reduce our error up to some numerical limit. And we can see increasing the truncation also increases the error since we are losing more information. To compare our actual reduction, we can take a 0.1% predefined error and see the reduction obtained by each order that can achieve this 0.1% error. And this is the graph. As we can see, our reduction increases as we increase the order up to some diminishing returns, since after some point adding a new approximation order also means you're adding a new system matrix to storage. However, we can still see that we can obtain better results than all that is already available in the literature. And the next example, we look at the pulsating sphere or the exterior example. Again, looking at the 3 points with the same error metric. We can see our reduction this time is not monotonic, but it also starts from an already high reduction at the first order, but we can still increase it, but we just need a better representative distance choice since we have been using an average distance to expand this solution. However, for an exterior problem where our measurement points are away from our graph, we can see that our average distance is not very representative of the measurement points. But we can still obtain significant reductions without much problem. Now, lastly, a bit more complex example where there's an incoming plane wave to a shape that is very long in one dimension and short in the other dimension, since this will be a drawback of the method. And we can see that our reduction is quite limited, only about reaching a 50% reduction. This is due to the fact that we need information or the ways to travel from one end of the domain to the other end of the domain before start truncating. Otherwise, we lose causality and introduce diverging type errors into our reduction. And this type of less reduction causes our already high calculation number to not decrease considerably. And so we need to also deal with this unfavorable scaling of square of the degrees of freedom of the boundary elements. And for that, we are planning to do projection-based model order reduction, if applicable, to our transient bases and also our Taylor series bases separately, so that each can be reduced according to their types. And then next, we may need to increase our dimensionality from 2D to 3D to obtain more real-life solutions. And finally, to implement IGA to this workflow to obtain this IGA type workflow to go directly from CAD to our finite element solution or boundary element solution. IGA has possible problems with the boundary element as well. Since boundary element has weakly and strongly singular integration, it may become harder to deal with them with the higher order terms, and they each one need special care. So it limits the automatic integration of the shape functions. Also, the leaky solutions for the higher orders should be considered, since higher orders continuity of the IGA may be a big advantage in frequency domain analysis, but it causes problems for the time domain where the waves are propagating discontinuously, so it may cause leakage. And also there are general issues with multi-patch coupling that should be taken care of. In light of these possible problems, we have decided to try an alternative method called shifted boundary method that is used in finite elements, since it may not have these problems for the time domain analysis. And for more detail about the shifted boundary method, you can follow Dr. Candidate number 1 presentation. And thank you for your attention.